Good morning, everybody. Good night and good evening, no matter where you are. Today we are solving calculus, a very nice calculus question. We're not solving more than one, and it's very simple. I've written it in a simple way because I don't have space. We have to find y such that. Okay, so we have this graph here where there's a tank of water and there's a hole. This tank of water has a height of h. Starting from the origin, obviously, and there's a hole at y, at length, at height y. Water is coming out and it's covering some range under the influence of gravity, obviously, and we are asked to find the y such that the range is the maximum, the most it can be. And we're given one piece of information here, that's what we really need, the exit velocity. Of course, we're gonna get y in terms of h. Since h is a constant, y is a variable. So now, I'm going to go ahead and write the only kinematic equation we're going to use, and this is very useful. And if you don't know it already, my very good friend has a video on it, deriving all of them actually. And the one we're using today is delta x is equal to v initial, times time, plus half a t squared. And that's what we're gonna use today. Before we do so, it's better to find the domain of y, and that's very easy. It's from 0 to h. The minimum is 0, the max is h. So let's write that over here. Y is between 0 and h. Okay, so we're gonna use this one right here, and I'm gonna rearrange just a bit. So delta x is x final minus x initial equals the rest of this business. There you go, very nice. And I'm just gonna move x sub I, x initial, to the other side. We can just remove this, and that's it. So x final is equal to VIT plus half AT squared plus x sub I. And now, this is very important actually. We need to differentiate between position on the y-axis and position on the x-axis, the range. Okay, so let's write out equations for the horizontal and the vertical displacement, and then fill out the terms we already have the values of. Okay, so I've cleaned up everything here, and this is the current information. Y is between 0 and h, and our initial velocity, previously it was the exit velocity, is the square root of 64 times h minus y. Okay, so let's write them out. We'll have x sub f in the x direction is equal to, again, VIT plus half AT squared plus x sub I, again, in the x direction. Of course, here, the velocity and the acceleration will also be in the x direction. What's our initial position? Obviously, here on the horizontal axis, we start at the origin, 0. So this will be a 0. Assuming we're on Earth, we don't have horizontal velocity. Acceleration. We don't have horizontal acceleration. We don't just drift away like that. We fall, meaning our acceleration is also 0. What is our horizontal velocity? It must be this, since this is the exit velocity, and the exit velocity points horizontally. It doesn't go down. The only reason water goes down is because of gravity. So VI will be this object right here, and we can write it out as x sub fx is equal to, I'm going to take out the 64 since it's a perfect square, 4 times 8. The square root of 64 is 8, not 4. This will not affect the calculations. Moving on. H minus y multiplied by time. Alright, very nice. We have our horizontal displacement as a function of time and, the height. It will depend on the height. H here is a constant, of course. Now we're going to work on the vertical displacement. That would be x sub fy is equal to vi y times t plus half ay t squared plus x sub I y. Okay, first term, easy term. The initial vertical velocity, and that is 0. Water is pushed out purely horizontally, and so we can just say that this is 0. Our, acceleration, we're on Earth again, so that would be negative 9.8. So let's write that out. That would be negative 9.8, of course, over 2 times t squared. What's our initial height? And that would be y. Okay, very nice. So now we have our vertical displacement equation and our horizontal displacement equation. And now what we want here is the range. We need the maximum range. So we need to maximize this function over here, or this relation. No, it's a function. It is a function. Yes. Why am I doing this to myself? So now here we're asked for maximum range. So we're going to maximize this function right here. And it's a function of time and, height. So we're going to solve for time. How are we going to do that? Well, time of a falling object depends on the vertical displacement. Once an object lands on the ground, it doesn't move horizontally anymore. And so we're going to set x sub fy equal to 0. That is when the object falls to the ground. And then we're going to solve for time with respect to height. So that would be something like this plus y. And so time could be solved for like this. Let's do this, 2y over 9.8. And we're going to take the square root. Of course, the positive square root, negative time, does not make sense over here. And now we have an expression of time, of course, depending on the vertical displacement. And we're going to plug that in right here. Okay, so now our horizontal displacement, previously a function of 2 variables, is a function of 1 variable. The variable we care about. We're finding the y that maximizes the displacement. And that would be x fx of y is equal to 4 times the square root of h minus y times time, which is this object right here. And while I'm at it, I'll simplify. 2 over 9.8 is just 1 over 4.9. And that's it. So we have our h, a constant, and y, the variable that we're going to play around with. So if you want to find the maximum of a function, you have to find its derivative, and where the derivative is either undefined or 0, those are the extremum points. And then hopefully we'll find our maximum. But before, we'll simplify a bit. These are radicals, so we can combine them. And I'm going to take the square root of 4.9 outside, giving us, I'm leaving the subscript behind. This is a constant. These will multiply. And this is our simplified expression. So we're going to use the chain rule and the power rule and a bunch of stuff. So the derivative with respect to y will be a constant times, hy minus y squared, all to the half power. That's the radical over here. And so we're going to drop that down. We're going to minus 1, leaving us with a negative 1/2. And then we're going to multiply by the derivative of the inner, which I'll put down here, which will be y minus, h minus 2y. I'll rewrite, come back, hopefully. Okay, so to find our critical points, we'll see where the derivative is 0 or undefined. And we'll check, of course, our endpoints over here. So when is this undefined? Well, when the denominator is equal to 0. So we need to check out y times h minus y equal 0. Now we have two cases here where y is equal to 0, making this expression 0, and y is equal to h minus h is 0. Notice these are the endpoints, so we don't have to check more points. Okay, so when is our derivative equal to 0? Well, that's precisely when the numerator is equal to 0. And the numerator is 2 times h minus 2y. And we set that equal to 0. Of course, the 2 doesn't matter. And we end up solving for y. And over here we get y is equal to h over 2. So we'll check y equals 0, y equal h, and y equal h over 2. Then we find the maximum. Okay, so we have our critical points, 0, h, and h over 2. We're going to plug them in this position function with respect to y, because we don't have t. Plugging in 0, we'll get 0 times h minus 0, which is 0, times this, which is 0. So our x is equal to 0, 1y is equal to 0. And the same thing goes for y equal h. H minus h is 0, times h, again 0, and the whole will be 0. So x is 0 when y is equal to h. Leaving us with h over 2, which is the answer, but we can calculate it nonetheless. That'll be x equals 2 times the square root, 2 times 2 over the square root of 4.9, times, well, that'll be h over 2, times h minus h over 2, which will just be h over 2. And that'll be 2 over the square root of 4.9. H times h is h squared. 2 times 2 is 4. And after taking them out of the square root, we'll get this. We can cancel the 2's. And we'll get h over the square root of 4.9. And this will be the maximum displacement, maximum horizontal displacement. Disregarding my failure and replacing the 64 with a 16 in the exit velocity, yes, this is the correct answer. Otherwise known as the range, of course, occurring at y is equal to h over 2. Thank you so much for watching. I hope you come back after this video. Goodbye.